Whether you're building a game, analyzing data, or writing automation scripts, understanding how to manage collections of information is essential. This module focuses on two of Python's most important data structures: lists and dictionaries. These structures form the foundation of real-world programming, helping you store, update, and access information efficiently. Throughout this presentation, we'll explore common operations, built-in methods, and best practices for using both structures effectively. If you're just getting started with Python or looking to level up your code organization and logic, this tutorial will give you practical techniques you can apply immediately. Working with Lists and Dictionaries in Python by the Programming Professor. In this module, we'll take a structured look at how Python handles lists and dictionaries. You'll learn how to work with list methods, loops, nesting, slicing, list comprehensions, and sorting techniques. We'll also walk through command line argument handling using sys.argv. On the dictionary side, we'll cover how to create, update, and iterate through dictionaries, including nested dictionaries for modeling more complex data. Along the way, we'll highlight best practices and common pitfalls so you can write cleaner, more efficient Python code. Lists in Python are mutable, ordered containers capable of holding any type of data, including other lists. As a mutable data type, lists can be resized and modified in place, unlike strings or tuples. They're also ordered, meaning elements have a specific position and can be accessed by index. You can create lists using square brackets, like 1, 2, 3, or by calling the list constructor on any data type that can be iterated, such as a string or range. Lists are incredibly flexible. They can store elements of different types, and their dynamic nature makes them ideal for many programming tasks, from simple aggregations to complex data modeling. Understanding how lists behave as containers is fundamental for all higher-level Python work. Accessing list elements is done using indexing, where the index starts at 0. You use square brackets and an integer to access an element at a specific position. For example, index 0 retrieves the first item, and index 4 retrieves the fifth. You can also use variables as indices, as long as those variables evaluate to integers. Attempting to use a float or another type will raise a type error. This indexing behavior allows for dynamic element access in loops, functions, or interactive programs. Just remember that indices must always be within the bounds of the list's length. Accessing an index that doesn't exist will result in an index error. Python provides a wide range of list operations, many of which can modify the list directly or in place. For instance, you can update a value at a specific index using assignment, or delete an element using the del keyword. You can also concatenate lists using the plus operator, and slice them using start and end indices. In-place modifications are possible because lists are mutable, and this feature makes them powerful for iterative updates, filtering, and real-time data adjustments. However, you should be cautious. Changes made to a list in one part of a program may affect other parts if the same list is referenced in multiple places. One important concept when working with lists is the difference between copying a list and referencing it. Assigning one list to another using equals doesn't create a new copy. It creates a shared reference. This means if you change an element in one variable, the other reflects that change as well. To create a true copy, use the copy method or slice notation like list with colon in square brackets. This distinction is critical in scenarios where you want to preserve the original data while performing operations on a working version. Forgetting to create an independent copy can lead to unintended side effects, especially in functions or loops that modify lists. Python lists come with a powerful set of built-in methods that allow you to add, remove, sort, and examine elements efficiently. These methods are preferred over manual index manipulation because they express your intent more clearly and make your code easier to read and maintain. For example, instead of slicing and extending manually, you can use append, extend, or insert to add items. Similarly, you can remove elements using remove or pop rather than low-level constructs like del mylist of 0. It's helpful to understand which methods modify the list in place, such as sort and reverse, and which return new information, like count and index. These methods are not only more concise, but also reduce the risk of logic errors compared to manually managing indices or writing custom loops. To add elements to a list, Python provides several methods depending on your needs. The append method adds a single item to the end of the list. If you want to add multiple elements at once, extend takes another list and adds each of its elements to the end of the current list. Meanwhile, insert allows you to place a new item at a specific index, shifting subsequent elements to the right. These operations are useful in a variety of applications, from dynamically growing lists based on user input to building complex data structures. Understanding when to use each method ensures your lists grow in predictable and maintainable ways. Removing elements from a list is just as important as adding them. Python provides remove, which deletes the first matching value, and pop, which removes an element by index and also returns it. If no index is given, pop removes and returns the last element. This dual behavior is useful when you need both the updated list and the removed item, like when implementing undo functionality or moving data between structures. Keep in mind that remove only deletes the first occurrence of a value and raises an error if the value isn't found, so use it carefully. These methods allow for precise control over your data and are central to list cleanup and filtering operations. Sorting and reversing lists can be done in place using sort and reverse. The sort method arranges the list's elements in ascending order by default, while reverse flips the current order of elements. Because both operations modify the original list, they are efficient and memory-friendly, but you must be cautious if the original order matters elsewhere in your program. These methods are commonly used for preparing data before presentation, such as sorting scores, names, or dates. If you need to preserve the original list, consider using the built-in sorted function instead, which returns a new sorted list without affecting the original. In addition to modifying methods, lists also support non-modifying methods like index and count. The index method returns the index of the first occurrence of a specified value, which is useful when you need to locate data for conditional logic or updates. The count method tallies how many times a specific value appears in the list, helpful for validation, analytics, or input processing. These methods don't change the list. They simply provide information about its contents. Together, these non-destructive tools complement the modifying methods and help you gain insights into your data without altering it. To process each item in a list, Python provides the for loop, a fundamental tool for iteration. In this structure, each value in the list is automatically assigned to a loop variable, which you can then use inside the loop body. This eliminates the need to track indices manually. For example, if you're iterating over a list of numbers, each number is accessed in order, and the loop body runs once per item. This type of iteration is ideal for tasks like printing, computing aggregates, applying transformations, or filtering data. It's one of the most readable and Pythonic ways to access list elements, and is preferred over traditional index-based loops, unless index access is explicitly required. In cases where you do need access to both the index and the value during iteration, Python provides the built-in enumerate function. Using enumerate, you can loop through a list while keeping track of the position of each element. This helps avoid common errors like index misalignment or out-of-range exceptions. Instead of using a manual counter variable, enumerate returns a tuple for each item, containing both the index and the value. This pattern results in cleaner, more maintainable code and is especially useful in debugging, displaying item positions, or performing indexed updates within a loop. Python includes several built-in functions for common list processing tasks, offering more concise alternatives to traditional loops. The all function returns true if every element in the list is true, while any returns true if at least one element is. These are useful in validation checks or conditional workflows. Functions like max, min, and sum perform common aggregations with just one line of code. These are far more readable and efficient than writing your own loops. They also reduce the likelihood of bugs by abstracting away the loop logic. When possible, favor these built-in functions for cleaner, faster, and more expressive list operations. To summarize these list utilities, Python's built-in functions are optimized for both readability and performance. Use all when you need to verify that every condition in a list passes, like checking that all inputs are non-zero or all strings are non-empty. Use any when only one valid condition needs to be met. If you're comparing elements or preparing data for presentation, max and min help you find extremes. And for numeric data, sum provides a fast way to total values. These functions should be part of every Python programmer's toolkit. They simplify code and make your intentions clearer to readers. Lists in Python aren't limited to flat structures. They can also contain nested lists, where each element is itself a list. This allows you to create complex data structures like tables, matrices, or grids. For example, a list like 10,20 and 30,40 can represent 2 rows of data. You can access these elements using double indexing, where the first index retrieves the sublist, and the second retrieves the element within that sublist. This is the foundation for two-dimensional arrays in Python. Understanding how to navigate nested lists prepares you for tasks like table processing, game boards, and multi-dimensional data representation in simulations and modeling. Nested lists are incredibly useful when representing structured grids like tables, spreadsheets, or game boards. A common example is a tic-tac-toe board, which can be represented as a list of 3 lists, each holding 3 values, X, O, or a blank space. To access individual cells, you use 2 indices, the first for the row, the second for the column. For example, board of 1, 2 accesses the 3rd cell in the 2nd row. This structure lets you organize data spatially and makes your code easier to align with how humans naturally visualize grids. It's also scalable for larger boards or matrices, allowing for clear, logical representation of 2D data in both games and applications like CSV processing, simulations, or GUI layouts. Python doesn't limit you to just 2 levels of nesting. You can create lists within lists to any depth, leading to 3D or even higher dimensional structures. This is useful in specialized contexts like 3D simulations, voxel-based games, or representing time-based changes in multi-dimensional data. For example, a 3D list might be used to represent a cube of numeric values, where each index step drills into another layer of structure. Accessing deeply nested elements requires 1 index per level, like table 111. While powerful, deep nesting should be used with care. It's easy to lose track of what each index represents. When used thoughtfully, though, it unlocks the ability to model complex, real-world systems in code. To work with multi-dimensional structures, you'll often use nested loops. This pattern lets you iterate through each row and each column within that row. Python's enumerate function is especially helpful here, as it gives you both the index and value at each level. For example, when printing a currency conversion table, You can loop through each row using enumerate, currency, and then loop through the values in that row, also using enumerate. This pattern is common when working with data tables, game boards, or when rendering output in a formatted grid. The ability to access both the data and its position within the structure makes your loops more powerful and your code more expressive. Python lists also support slicing, which allows you to extract a subset of elements into a new list. This is similar to string slicing and uses the same syntax: list, start colon end. The slice includes elements from the start index up to, but not including end. This makes it easy to grab a chunk of data without modifying the original list. For example, if you have a list of scores, slicing from index 1 to 3 gives you the second and third scores. This technique is great for copying, trimming, or segmenting lists in a way that's clean, readable, and safe from unintended side effects, since slicing always returns a new list. Slicing is especially useful when you want to access specific portions of a list, whether it's the first 2 items, the last 3, or a middle segment. You can use index ranges like 0:2 to get the first 2 items, or 1:3 to get the second and third. If you want to include the final element, the end index must go 1 past the actual last index. These patterns are common in data processing, such as previewing the first few records of a dataset or skipping headers. Using slices makes your code more concise than using loops or manual list construction, and it ensures your logic stays readable and consistent across different tasks. Slicing in Python also supports negative indices, which count backward from the end of the list. This is especially helpful when working with lists of unknown or variable length, where you may want to access items relative to the end rather than the beginning. For example, my list of -1 gives you the last element, and a slice like 0:1 returns all elements except the last. You can combine negative start and end values to extract segments from the tail of the list. These techniques are commonly used when trimming trailing values, removing padding, or slicing off extensions from file paths. Mastering negative indices allows for much more flexible and dynamic list handling, particularly in applications like parsing, data cleaning, or working with logs and datasets of variable size. In addition to start and end, Python slicing supports a stride, the step size between elements. This is specified using the syntax list start:"end:"stride. For instance, a stride of 2 skips every other element, while a stride of -1 reverses the list. This makes slicing incredibly powerful for sampling, skipping, or reversing data. It eliminates the need for explicit loops in many cases, and offers a more concise way to express common patterns like selecting every third value or processing elements in reverse. Understanding how to control the stride allows you to work efficiently with time series data, alternating elements, or reverse sequences, all with a single, elegant line of code. There are a number of common slicing patterns that you'll find useful across many Python programs. These include slicing from the start up to a certain index, from a certain index to the end, or selecting the entire list using a colon in square brackets. You can also combine start, end, and stride to extract more complex segments, such as 0:5:2 to get every second element from the first 5. These patterns help reduce repetitive code and improve clarity, especially when working with input sanitization, batch processing, or segmenting datasets. Since slicing returns a copy of the original list, it's a safe operation that avoids unintended changes to the source data. Familiarity with these patterns makes your Python code more concise and readable. There are times when you'll need to modify elements in a list while looping through it, such as applying a transformation or adjustment to each item. One safe and effective way to do this is by using an index-based for loop with range, len, my list. This approach gives you direct access to each index and allows you to update elements in place. For example, adding 5 to each value in a list of numbers can be done efficiently by referencing each index in turn. This is particularly useful in data normalization, scaling, or when working with sensor readings and financial values. Since you're modifying the list in place, it's important to be intentional about how you loop to avoid introducing bugs or overwriting values unintentionally. Modifying the size of a list while iterating through it can be risky and often leads to logic errors or skipped elements. This is because removing items shifts the positions of remaining elements, which can throw off your iteration. A common mistake is to use a for loop directly on the original list, while simultaneously deleting items. A safer alternative is to iterate over a copy of the list using slicing, my list with a colon in square brackets, so the iteration isn't affected by changes to the original. This approach allows you to filter out elements, move data between lists, or apply transformations without corrupting the iteration process. Using list copies when modifying during iteration is an essential practice for writing safe and predictable code. Python offers a concise and expressive syntax for building new lists called list comprehensions. Instead of writing a full loop with append, you can create a list in a single line using a comprehension that combines a loop and an expression. For example, to add 10 to every number in a list, you can write n plus 10 for n in nums. This approach improves readability and eliminates boilerplate code. Comprehensions are ideal when you want to transform or filter data during list construction, especially when working with input processing, data cleaning, or reshaping existing lists. They're widely used in both small scripts and large-scale data pipelines because of their clarity and efficiency. List comprehensions can replace many standard for loop patterns and often result in shorter, faster, and more readable code. For instance, you can convert all elements in a list to strings, transform user input into a list of integers, or even compute row-wise totals in a two-dimensional list, all in one line each. This makes your code more declarative, focusing on what you want rather than how to do it. You can also embed list comprehensions inside functions, or use them in conjunction with other functions like min, max, or sum. As your projects grow more complex, adopting comprehensions will help you write cleaner code that's easier to debug and maintain. Python also supports conditional list comprehensions, allowing you to include an if clause at the end to filter which items are added to the new list. This is useful when you want to build a list from another list, but only include elements that meet a certain condition. For example, n for n in numbers if n modulo 2 equals 0 gives you a list of even numbers. This is much cleaner than writing a full loop with an if statement and a call to append. It's especially helpful in data processing or real-time filtering scenarios, where clarity and speed are important. Conditional comprehensions not only improve readability, but also ensure you don't accidentally carry over unwanted elements into your results. To sort the elements of a list in place, Python provides the sort method. This method modifies the original list and arranges its elements in ascending order by default. A practical example is sorting book titles entered by the user. The list of titles is built dynamically, and once all the input is collected, sort is called to arrange them alphabetically. This is an efficient way to organize data for display or export. It's important to note that sort changes the original list. If you need to keep the unsorted version, you'll want to use sorted instead. Sorting is fundamental in many applications like data reporting, search, and UI elements like drop-down lists. In contrast to sort, the built-in sorted function creates a new sorted list, preserving the original. This is particularly useful when you want to display a sorted version of a list, but still need to access the original order later. For example, when processing numbers from user input, sorted gives you a neatly ordered list without affecting the one you originally stored. This technique is useful in applications where the same data must be presented in different ways, or when one operation requires sorted data but others rely on the original sequence. Using sorted over sort is a best practice when data integrity or non-destructive behavior is a concern. When sorting lists, you can make the results more flexible and meaningful by using the key equals parameter. This lets you define a custom sorting behavior by passing in a function that's applied to each element before comparison. A common example is case-insensitive sorting, where strings are sorted using str.lower to ensure consistent alphabetical order regardless of capitalization. You can also sort by string length using key equals len, or sort a list of tuples or nested lists based on a particular value. This feature is powerful when working with data that includes mixed capitalization, nested elements, or when sorting depends on a specific property rather than the raw value. It makes your sorting logic more adaptable and your code more reusable in real-world applications. In addition to customizing how items are sorted, you can also control the direction of the sort using the reverse equals true flag. By default, sorting is in ascending order, but setting reverse equals true allows you to sort from highest to lowest. This is useful for showing top scores, recent dates, or highest values first. Whether you're sorting a list of numbers or strings, this simple flag lets you reverse the order without writing a separate step. You can also combine reverse equals true with key equals for advanced sorting, like sorting names by length in descending order. This makes sorting both powerful and concise, helping you tailor your data output to match your program's goals or user expectations. As your Python programs grow beyond basic scripts, you may need to work with command line arguments. These are inputs the user provides when launching the program from a terminal, and they're accessed through the sys.argv list. The first element, sys.argv of 0, is always the program's file name, and any additional inputs are stored as strings in the remaining positions. To use this feature, you'll need to import the sys module. Command line arguments let users pass file names, options, or data directly to your program, enabling automation and integration into larger workflows. They're especially useful in scripts that are part of data pipelines, batch jobs, or system tools. Command line arguments let you pass input to your Python program when you launch it from the terminal, and Python provides access to them using sys.argv. This example demonstrates a simple use case: greeting a user based on their name and age, both provided as command line arguments. The program begins by importing the sys module, then retrieves the user's name and age using sys.argv of 1 and sys.argv of 2. The name remains a string, but the age is converted to an integer using int before being used. This example shows how easy it is to write interactive scripts that accept dynamic input at runtime. However, there's a catch. If the user forgets to provide both arguments, Python will raise an index error. That's why it's important to validate the number of arguments before accessing them. While this example is simple, it illustrates how command line arguments can make your Python programs more flexible and automation-friendly, especially when integrating scripts into workflows or passing parameters from external tools. When using sys.argv, it's important to validate the number of arguments before accessing them. If your program expects 2 inputs and the user only provides 1, you'll get an index error. The best practice is to check len, sys.argv at the start of your program and exit gracefully with a helpful usage message if the required arguments are missing. This makes your program more robust and user-friendly. For example, a greeting script that takes a name and an age should verify that exactly 3 arguments are passed, Then convert the age from string to integer before proceeding. Using sys.exit after an error message ensures the program stops cleanly. This kind of input validation is critical in professional development environments where your script may be reused or automated. Another important aspect of working with command line arguments is understanding that all values are strings by default. If you're expecting a number, like an age or a count, you'll need to explicitly convert it using int or float. Additionally, if a user inputs multiple words, each space-separated part is treated as a separate argument. To group them into one, users must wrap the text in quotes. For instance, Mary Jane enclosed with double quotes will be interpreted as a single argument, while Mary Jane without the double quotes would be treated as two. This has real-world implications when dealing with names, file paths, or descriptions passed into your program. Understanding and handling these edge cases ensures your scripts work reliably no matter how users provide input. Python's dictionary type is a powerful tool for storing and accessing data using keys rather than numeric indices. Unlike lists, which are ordered sequences of values, dictionaries are collections of key-value pairs. Each key maps to a specific value, and keys must be immutable types like strings, numbers, or tuples. Dictionaries are ideal when you want to look up data quickly based on a label or name. For example, associating student names with grades or product names with prices. Since Python 3.7, dictionaries also maintain insertion order, which means the order you add elements is preserved when iterating. This makes them more predictable for reporting and structured output while retaining the speed and flexibility of key-based access. There are several ways to create dictionaries in Python, each suited to a different situation. The most common is using curly braces with key-value pairs, like Jose:(A+) and Gino:(C-). You can also use the dict constructor with keyword arguments, such as dict Bobby equals 55552232, or pass in a list of tuples to dict for more dynamic creation. This flexibility makes it easy to generate dictionaries from user input, CSV rows, or database records. Regardless of how you define them, dictionaries are an essential data structure in Python, and understanding how to create them in different ways helps you adapt your code to a wide variety of input formats and data sources. Dictionaries are mutable, meaning you can update, add, or delete entries at any time. You can access values using square brackets with a key, just like you'd access a list item by index. Assigning a new value to a key updates it, and using del removes the key entirely. You can also check if a key exists using the in keyword, which is useful for conditionally updating or retrieving values. Beyond storing simple values like strings or numbers, dictionaries can store more complex types, including lists, other dictionaries, or custom objects. This makes them ideal for representing structured records like a student profile, an API response, or a shopping cart. Knowing how to manipulate dictionaries in place is fundamental for building dynamic and interactive Python programs. Python dictionaries also include a variety of built-in methods for managing their contents. For example, clear removes all key-value pairs, essentially resetting the dictionary. The get method allows you to safely access a value without risking a key error, and you can even provide a default value to return if the key doesn't exist. The update method merges another dictionary into the current one, adding or overwriting keys as needed. Finally, pop removes a key and returns its value, which is useful when you want to delete and use data at the same time. These methods make it easy to manage dictionary data without manually checking for key existence or writing complex logic. They also support more readable and efficient code in real-world scenarios, like merging configuration files or processing structured input. Like lists, dictionaries are referenced by assignment, meaning that assigning a dictionary to another variable creates a shared reference, not a copy. If you modify the dictionary through one variable, the changes are reflected in the other. For instance, removing a key using pop on one variable will affect the dictionary referenced by the other. This behavior is useful for sharing data between functions or storing configurations, but it can also lead to bugs if you accidentally modify a shared structure. If you need to work with an independent copy, you should use the copy method or the dict constructor. Understanding the difference between a reference and a copy helps you avoid unintended side effects and keeps your code predictable and bug-free. You can iterate over a dictionary using a for loop, which retrieves one key at a time by default. Inside the loop, you can access the corresponding value using my dict with key in square brackets. Remember that starting in Python 3.7, dictionaries preserve the order in which keys were inserted, so iteration order will match the order of addition. This is helpful for ordered output, like displaying menu items or structured reports. Internally, Python dictionaries use hash tables for fast key lookup, which makes access and updates efficient even for large datasets. This basic key-based iteration pattern is foundational for filtering, updating, or formatting dictionary contents in your applications. Python dictionaries also offer view-based iteration through the items, keys, and values methods. The items method returns both the key and value for each entry, which is useful for situations where you need full access to each pair, such as displaying data or transforming it into another format. The keys method returns just the keys, while values gives you only the values. These views are dynamic. They reflect changes to the dictionary in real time. This makes them useful when iterating over large dictionaries that might change during execution. Whether you need to inspect keys, values, or both, these methods provide clear, semantic ways to access and work with dictionary contents. Dictionary view objects, like those returned by values or items, are not directly indexable. If you want to sort, slice, or access elements by index, you must first convert the view to a list using list. This is especially useful when you want to analyze dictionary content, such as finding the closest or largest values. For example, you might extract distances from a dictionary, sort them, and pick the smallest two values. Converting views to lists gives you access to Python's powerful list tools, including slicing, indexing, and comprehensions. This conversion is common in data analysis, reporting, and any application that combines dictionary lookups with list-style data processing. Python supports nested dictionaries, where the value associated with a key is itself another dictionary. This structure is incredibly useful for representing complex, structured data, like records, configuration files, or grouped attributes. For example, you could have a student's dictionary, where each student name maps to another dictionary containing their grade and student ID. Accessing nested values requires multiple bracket levels, such as student's Jose grade. This hierarchical layout mirrors how data is organized in JSON, databases, and structured file formats. Understanding how to store and access nested dictionaries is essential when working with data pulled from APIs or external sources, or when building applications that manage multi-field records. Nested dictionaries also allow for modeling more detailed records, like a gradebook. In this example, each student maps to a dictionary that includes lists of homework scores and values for midterm and final exams. The program prompts the user for a name and, if found, prints out each homework score, the midterm, and the final, then calculates a percentage based on a total of 500 possible points. This pattern mirrors real-world data systems where each entry contains subfields. Iterating through these subfields using loops and functions like enumerate provides fine-grained control and allows your program to scale as data complexity increases. This structure is perfect for applications involving user profiles, academic records, product catalogs, and more. When working with deeply nested dictionaries, maintaining clear layout and consistent indentation is crucial for readability and maintainability. Descriptive keys like homeworks or final make the data easier to understand at a glance. It's also helpful to avoid unnecessary levels of nesting. Deep nesting can make access logic complicated and increase the risk of bugs. In situations where nested access is unavoidable, consider structuring your code to reduce depth or write helper functions to extract values cleanly. In Python, dictionaries can be nested as deeply as needed, but best practice is to prioritize clarity. When dictionaries are well organized, they become powerful tools for modeling structured data with complex relationships. To close out this module, we reflect on the core takeaways. Lists allow you to store and manipulate ordered collections of data, offering powerful tools like slicing, comprehensions, and built-in utility functions. You've learned how to iterate through them, modify them in place, and even nest them to build grids or multi-dimensional structures. On the other hand, dictionaries provide a way to associate keys with values, making them perfect for lookups, structured data, and records. You've seen how to add, update, and iterate through dictionaries, use nested dictionaries for complex structures, and apply methods that make them flexible and robust. Together, lists and dictionaries form the backbone of most real-world Python programs. Mastering them gives you the tools to build scalable, efficient, and readable code, no matter what problem you're trying to solve. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.